Ratuna Şahin, I know.
Zeynep.
Today we will be presenting our group's EMT project, which is an EMP generator. We will first go over what EMPs are, and we will then go ahead and talk about how they work and the theory behind them. We will then talk about the process of making our setup, and we will discuss our results. EMPs are also referred to as transient electromagnetic disturbances, are sudden bursts of EM fields which cause disturbances or interference in the other electromagnetic phenomena around them. They can be both natural and artificial. For example, lightning strike is also an EMP source which causes atmospheric noises, and it's a common interference. To build our EMP generator, we will use this setup, which is a simplified diagram. We will use a 400 kilovolt boost converter that will allow us to charge energy in this capacitor. We will discharge this energy suddenly through this spark gap, which will then radiate B fields from this coil. As we said, we need to radiate B fields. We will use a coil which radiates B fields with sudden current changes. The B field per current can be obtained from this formula using Biot-Savart law. And we have 80 windings on our coil, so we will have 80 times this magnetic field. And to obtain the current in question, we need to charge the capacitor as discussed and discharge it quickly. We will charge the capacitor until a certain voltage, until it is enough to ionize the air in the spark gap. Once the air is ionized, its resistance drops significantly, and this allows for the discharge on the capacitor. Therefore, as you can see, this is the current transfer function. Higher the voltage of the capacitor, higher the current. However, higher the voltage, the longer it takes for our capacitor to reach that voltage. So we have a trade-off between EMP intensity and EMP firing rate. Finally, to obtain this current, we will use an RLC circuit. Air ionizes at around 3 kilovolts per millimeter, and our spark gap is 5 millimeters in length. So we will need 15 kilovolts in our capacitor. And the resistance of the circuit can be calculated from the resistivity and the terminal width and the length as 3.86 along with the resistance of our inductor, and our capacitances and inductances are as shown. Using the transfer function from the previous slide, we can obtain the current as a function of like this, with damping ratio 0.101 and frequency 150 kilohertz. Finally, we will test our circuit with a coherer. Coherers are primitive radio frequency detection tools that were used in the beginning of 20th century. They house metal filings between two terminals, and once these metal filings detect electromagnetic waves, they become much more conductive, allowing for the measuring of the presence of EM fields. This contraption will be used to measure the EM fields from our EMP generator. And my friend Zeynep will take over.
Now I'm going to explain the development process and some of the measurements. We divide the development process to 4 parts, which are building the capacitor, making the spark plug, winding the radiating coil, and making the coherer. While building the capacitor, we use cellulose acetate sheets as our dielectric video, which has a relative permittivity of 4.87 and width of 120 micrometers. Also, we use aluminum layers by lefting a 0.5 centimeter margin from all of the sides, and the area is resulted by like 0.057 meters square. We place the two A4 cellulose acetate sheets between the aluminum layers, and the distance between the capacitor plates is measured to be 240 micrometers. By using this capacitance formula, we find the theoretical capacitance to be 10.3 nanofarads, and when we measured it with our multimeter, we measured it to be 9.86 nanofarads with an error of 4.2%. This can be because of a dust stack between the layers or the aluminum foils not being perfectly flat, and because of these errors, the fringe risk increased. Then for the spark plug part, we used 2 copper wires with a width of 1 millimeter. We inserted them inside of a plastic container for the safety risk, since there's going to be 15 kilovolt in there. And also, we adjust the distance between the wires, spark gap, by trial and error and our intuition. As Tuna said in the previous part, the trade-off between the pulse intensity and pulse firing rate is adjust. Then we want the radiating coil, we want 80 windings, and we measured the inductance to be 140 microhenry. We were very careful for the windings to be neat and tight to reduce the risk of magnetic field leakage. Also, we add an extra layer of a tape to isolate the system more and for mechanical stability. Then, for the testing part, we use coherer as mentioned before. To make the coherer, we use aluminum foil balls as our metal fillings. And then we inserted them inside of a plastic container, and we connected two aluminum terminals to the two sides of the container. And then we connected our multimeter to the resistance node to see if there's a short circuit or not.
So for our cost part, we bought 4 acetate sheets. Each of them costed 17 liras. And we bought a boost converter that converts 4 volts to 400 kilovolts. And all other equipments were our, because we used them in our old projects. So our total cost was around 430 liras. For safety, as I said, we are using 400 kilovolts, and which is pretty dangerous, and we have a lot of arcs going on. And because of that, we made a safety container to put the arc in. You can see in the other pictures. And because we are using an EMP device, we kept our technological devices away from our project so they wouldn't disturb it. Let us discuss the results. This is our final demo of the project. As you can see, there's the coil, there's the capacitor, there's the spark gap and our boost converter, and this is a switch for safety. Then we used oscilloscope to measure the induced voltage on the coil. As you can see, it's being damped and it's a sinusoidal, which has a frequency of 140 kilohertz. But when we did the RLC circuit in AltaSpice, we found it was 150 kilohertz. And we think that the difference of 10 kilohertz is because of the parasitic capacitance and parasitic things on the wires, and the coil itself has a self-capacitance. And also our damping ratio was 0.2, while the theoretical was 0.1. The same cause of errors are still here. And this is our induced voltage in the oscilloscope yet, and our induced voltage in the AltaSpice calculations. And this is a video of our test with calculator. Would you like to watch it, or we can demonstrate it in the
Demonstrations.
Okay. This part is again a demonstration, and this is about it.